All right, so let's take a look at that data that we've collected from our experiment just a few days ago. You get out that sheet and turn it over onto the back where you'll see this data table. I'm going to start with trial 1, where we had 10 milliliters of HCl, 20 milliliters of hypo for a grand total volume of 30 milliliters. And you'll recall that we suggested that all these volumes, total volumes, should be kept at 30. Keep that variable constant. And when we did that, we got some times. I want you to calculate, please, that average time. It's usually somewhere around 30 seconds for that first mixture from year to year. You can calculate what our exact class average is from your class data. Right now, I'm more interested in the columns with concentration. You remember those brackets? We need molar concentration, moles per liter of hypo, and moles per liter of HCl, two columns that are completely blank. So in the first mixture, we had 10 milliliters of HCl, and its initial concentration was 0.5 molar. So I'm going to start with 0.5 molar. And we took that 10 milliliters and diluted with 20 milliliters of hypo because the hypo has no HCl in it. So effectively, we're diluting 10 milliliters to 30, and that reduces our concentration by 1/3, 10/30ths. And the effective concentration of the HCl in the solution then after the two solutions are mixed is going to be equal to 1/3 of 0.5, which is approximately 0.17 molar to two significant figures. Using the same rationale for our hypo, it started out at 0.2 molar, and we diluted it. Let's see, we started with 20 milliliters and diluted to a total volume of 30 by adding 10 milliliters of HCl, so that would be 20/30ths as concentrated as the original solution, and 20/30ths of 0.2 is going to be 0.1, let's see, 0.2, that's about 0.13 molar. There we go, 2/3 of 20, 13. All right, so there we've got our two concentrations, HCl and hypo, in trial number 1. Well, let's look at trial number 2. In trial number 2, we had only 5 milliliters of HCl and a total volume of 30 with 5 milliliters of water. That must mean 20 milliliters of hypo again. So you see, we didn't vary the amount of hypo in trials 1 and 2. We varied the amount of HCl. We had the amount, so not surprisingly, the concentration of HCl will be 0.5 molar times 5 milliliters, that's what we used, diluted to a total volume of 30, 5/30ths. That is half of this concentration, which will be approximately 0.085 molar. And the hypo concentration, we started with 20 milliliters, just as in trial number 1, diluted to a total volume of 30. So its concentration is 0.13 molar, just like trial 1 is. No change in that concentration. Now, on our data, that was kind of interesting. I think our data shows approximately 35 seconds. There's not a very substantial change in the time of that reaction for reaction number 2, for trial number 2. But when we go to trial number 3, we'll start to see some very interesting things taking place. Because you see in trial 3, of course, we've got 10 milliliters of hypo as we had in trial number 1. So that would give us a concentration of, 10 milliliters of HCl, of course, which gives us a concentration of 0.17 molar. But now our hypo has been reduced to 10 milliliters, and that will of course then be a concentration of 0.2 molar times the ratio of 10 we had over the total volume, 30. And when we calculate that, we end up with half the concentration, approximately 0.065 molar hypo. And when we did that, the approximate time there from year to year, and your class data might be slightly different, is about 65 seconds. Now, interestingly, changing the HCl concentration did not affect the time that much. That means that the concentration of HCl, according to our experiment, does not change the rate of the reaction. The speed at which that sulfur is produced is not as dependent on HCl as it is on hypo, because you see quite a considerable change in time for the variation in the hypo concentration when we did that from trials 1 to 3. Again, I'm always using trial number 1 as more or less my control. Now you might wonder what this last column is. This is the rate of the reaction, and the rate of any reaction is inversely proportional to the time. So the more time the reaction takes, the slower the reaction is. As the time goes up, the reaction speed goes down. And that is why it's an inverse relationship. One's going up, that being time, the other, the rate goes down. So one way to approximate the rate here is to say that it's approximately equal to 1 over the time. That would be 1 over 30. I'll just fix that. These technological brains, I tell you, if you're not doing the right thing, there we go. So 1 over 30 seconds is a rate of 1/30th is 0.033 per second, or reciprocal seconds. Seconds to the -1. 1 over 35 for my second experiment, I'm just calculating that, is a slightly smaller number, but not very much smaller. If I just get my calculator out here, I can calculate that rather quickly. 1 over 35. Well, that is 0.028 seconds to the -1. And my 1 over 65 for my last trial is a considerably slower rate of reaction. 1 over 65. That's 0.015. So I have concentrations of HCl, concentrations of hypo, and rates of reaction. Now the next part of the experiment is to go to page 2, actually the bottom of page 1 where you've got your analysis section. In problem number 2, at the bottom of that page, you see that it says in 2 trials you can look at the difference in the initial concentration of hypo. So let's look at that hypo concentration. Here we've got a hypo concentration, trials 1 and 2, that are both 0.13, so there's no change there. If I go from experiment 1 to experiment 3, however, I notice that hypo's concentration halves in going from 1 to 3. Or if you want to think about it a little differently, the concentration of hypo is doubling if you go from experiment 3 to experiment 1. So I take a different color and I just look at that. From experiment 3, trial 3 to trial 1, I have a doubling of hypoconcentration. I'm interested, since HCl concentration stayed the same or constant during that time, and I'm going to mark that as it didn't change from experiments 1 to 3. I'm curious how the rate changed in going from experiment 3 to experiment 1. So just take a look at those two rate numbers, 0.015 per second, 0.033. Well, to me, that looks like about a doubling, because 15 times 2 is 30, and 0.015 times 2 will be about 0.030. So it looks to me like there's a doubling in the rate as well. Whenever the concentration of a reactant doubles, and it does exactly the same thing, doubles the rate of the reaction, we have a special name for that. That's called order number 1. When concentration change in hypo doubles and rate doubles, we call that first order. In other words, anytime the concentration change mimics the rate change, they occur by the same proportion, then we call it a first order reaction. If we do the same kind of thing with HCl and try to find a trial where HCl changes, this is like the second page now of your lab, so get your second page out. This is questions number 3 at the top of that second page. Find trials where the concentration of hypo remains the same, but the concentration of HCl changes. Well, notice in trials 2 and 1, I have a doubling of HCl. HCl doubles from 2 to 1. Concentration doubles. Notice hypo from 2 to 1 stays constant.